Download this code from codegive.com, link in the description below. OK, let's dive into context-free grammars, CFGs, and their implementation in Python, specifically targeting the concepts covered in VTU's 18 CS54 Module 3, Lecture 1. This tutorial will be comprehensive, covering definitions, examples, parsing techniques, and code implementations. VTU 18 CS54 Module 3, Lecture 1, Context-Free Grammars, CFGs. This lecture typically covers the basics of CFGs, including definition of CFGs, components, formal definition, G equals, V, T, P, S. Derivations, leftmost and rightmost derivations. Parse trees, representing derivations graphically. Ambiguity, grammars that produce multiple parse trees for a single string. Applications, basic application of CFGs in language processing. Simplification of CFGs, remove useless, unreachable, and unproductive symbols. Remove unit productions, and null productions. 1. What is a context-free grammar, CFG? A context-free grammar is a formal grammar used to describe the syntax of a programming language or other formal language. Context-free means that the application of a production rule doesn't depend on the surrounding symbols. This makes them much simpler to handle than context-sensitive grammars. 1.1 Formal definition. A CFG is defined by a for-tuple. *v*, a finite set of variables, or non-terminal symbols. These represent syntactic categories, example statement, expression, term. *t*, a finite set of terminals. These are the basic symbols of the language, example ID, plus, asterisk, if, else. V and T are disjoint, they don't share any symbols. *p*, a finite set of production rules. Each rule has the form a-alpha, where a is a variable, from v, and alpha is a string of variables and terminals, from, v union set symbol t, asterisk. S the start variable. This is a distinguished variable in v, usually representing the top-level construct of the language, example program. Example asterisk. Let's define a simple CFG for arithmetic expressions. *v equals e, t, f, expression, term, factor. *t equals id, plus, identifier, plus, multiply, left paren, right paren. *s equals e, the start symbol is expression. *p equals *e plus t. *e dash t. *t dash t f. *t dash f. *f dash e. *f dash id. 2. Derivations. A derivation is a sequence of rule applications that transform the start variable into a string of terminals. Direct derivation, equals we say that alpha a beta directly derives alpha gamma beta, written alpha a beta equals alpha gamma beta, if there is a production rule a dash gamma in p alpha and beta are strings of terminals and non-terminals. Derivation, equals, the derivation relation equals asterisk is the reflexive and transitive closure of the equals relation. That is, alpha equals asterisk beta if there exists a sequence alpha equals alpha 1 equals alpha 2 equals alpha n equals beta for some n equals 0. If n equals 0, then alpha equals beta. 2.1 Leftmost derivation. In a leftmost derivation, at each step, we replace the leftmost variable with the right-hand side of a production rule. Example, using the grammar above. Let's derive the string id plus id asterisk id using a leftmost derivation. 1 e equals e plus t, rule, e dash e plus t. 2 equals t plus t, rule, e dash t. 3 equals f plus t, rule, t dash f. 4 equals id plus t, rule, f dash id. 5 equals id plus t asterisk f, rule, t dash t asterisk f. 6 equals id plus f asterisk f, rule, t dash f. 7 equals id plus id asterisk f, rule, f dash id. 8 equals id plus id asterisk id, rule, f dash id. 2.2. Rightmost derivation. In a rightmost derivation, we replace the rightmost variable at each step. Example, using the same grammar and string. 1 e equals e plus t. 2 equals e plus t asterisk f. 3 equals e plus t asterisk id. 4 equals e plus f asterisk id. 5 equals e plus id asterisk id. 6 equals t plus id asterisk id. 7 equals f plus id asterisk id. 8 equals id plus id asterisk id. 3. Parse trees. A parse tree, or derivation tree, is a graphical representation of a derivation. Asterisk the root of the tree is the start variable. Asterisk each internal node represents a variable. Asterisk the children of an internal node represent the symbols on the right-hand side of the production rule used to expand that variable. Asterisk the leaves of the tree are the terminals. Asterisk reading the leaves from left to right gives the derived string. Example, parse tree for id plus id asterisk id based on the grammar. 4. Ambiguity. A grammar is ambiguous if there exists a string that has two or more different parse trees, or, equivalently, two or more different leftmost or rightmost derivations. Example, ambiguous grammar. Consider this simplified grammar. Asterisk e dash e plus e. Asterisk e dash e asterisk e. Asterisk e dash id. The string id plus id asterisk id has two parse trees. Parse tree 1, associating plus first. Parse tree 2, associating asterisk first. The two parse trees represent different operator precedence, addition before multiplication in one, multiplication before addition in the other. This ambiguity is undesirable, especially in programming languages. Grammars for programming languages are usually designed to be unambiguous. 5. Applications of CFGs. Asterisk syntax analysis. Parsing CFGs are the foundation for parsers in compilers. Parsers take a program's source code and build a parse tree, verifying that the code conforms to the grammar of the programming language. Asterisk language design. Asterisk CFGs provide a precise way to define the syntax of a language. Asterisk document structure. Asterisk CFGs can be used to represent the structure of documents like XML and HTML. Asterisk natural language processing. NLP. CFGs are used in NLP to model the syntax of natural languages, although more advanced formalisms are often required to handle the complexities of human language. Asterisk data validation. Asterisk defines CFGs to enforce rules on data structure. 6. Simplification of CFGs. Simplification aims to make a grammar more efficient or easier to work with without changing the language it generates. 6.1. Removing useless symbols. A symbol X is useless if it cannot appear in any derivation of a terminal string from the start symbol S. A useless symbol can either be unreachable from the start symbol, or does not derive any terminal string. Steps to remove useless symbols. Asterisk. 1. Remove unproductive symbols. Asterisk. A symbol X is productive if it can derive a string of terminals. Find all productive symbols. Remove all non-productive symbols and their productions. 2. Remove unreachable symbols. Asterisk. A symbol X is reachable if it can be derived from the start symbol S. Find all reachable symbols. Remove all unreachable symbols and their productions. 6.2. Removing unit productions. A unit production is a production of the form A-B, where A and B are variables. Unit productions can often be eliminated without changing the language. Algorithm asterisk. 1. For each variable A, compute the set of variables B such that A equals asterisk B using only unit productions. 2. For each variable A, and for each production B dash alpha where B is in the set computed in step 1, add the production A dash alpha to the grammar, unless it is a unit production. 3. Remove all unit productions. 6.3. Removing null productions. A null production is a production of the form A-epsilon, where epsilon represents the empty string. Null productions can also often be eliminated, but the process is a bit more involved. Algorithm asterisk. 1. Identify nullable variables. A variable A is nullable if it can derive the empty string, i.e., A equals asterisk epsilon. This is initially all variables that have a production A-epsilon. Keep adding variables until no new nullable variables are found. 2. For each production A-alpha, where alpha contains nullable variables, create new productions by replacing some or all occurrences of nullable variables with epsilon. 3. Remove all null productions A-epsilon, except if the start symbol S is nullable and S does not appear on the right-hand side of any production. 7. Python code implementation, basic parsing. Here's a basic Python implementation for representing CFGs and doing simple parsing, top-down, recursive descent. Explanation of the code asterisk. 1. CFG class asterisk. Asterisk represents a context-free grammar. Asterisk stores the variables, terminals, productions, as a dictionary, and the start variable. Asterisk the __str__ method provides a user-friendly string representation of the grammar. 2. Parse, CFG, input _string, function asterisk. Asterisk the main function that attempts to parse the input string according to the given CFG. Asterisk splits the input string into a list of tokens, assuming tokens are separated by spaces. Asterisk calls the parse _variable function to recursively check if the string can be derived from the start variable. 3. Parse _variable, variable, remaining _input, function, recursive descent. Asterisk this is the core of the parser. It tries to match the given variable against the remaining input. Asterisk it iterates through the productions for the given variable. Asterisk for each production. Asterisk it splits the right-hand side of the production into a list of symbols. Asterisk it iterates through the symbols in the production. Asterisk if the symbol is a terminal, it checks if the next token in the input matches the terminal. If not, the production fails. Asterisk if the symbol is a variable, it recursively calls parse _variable to try to parse the variable against the remaining input. If the recursive call fails, the production fails. Asterisk if all symbols in the production are successfully matched, the production succeeds, and the function returns true. Asterisk if no production can be successfully matched, the function returns false. Important considerations and improvements asterisk. Asterisk error handling asterisk the current parser provides very basic error reporting, simply false. A more robust parser would provide more informative error messages, such as the expected token or the location of the error. Asterisk ambiguity asterisk this parser doesn't handle ambiguity gracefully. It will only find one possible derivation. For ambiguous grammars, you'd need to use techniques like early parsing or CYK parsing. Asterisk left recursion asterisk the recursive descent parser will fail for left recursive grammars, example E-E plus T. To handle left recursion, you need to transform the grammar to eliminate left recursion. Asterisk tokenization asterisk the current code assumes the input string is already tokenized. In a real compiler, you would need a separate tokenizer, lexical analyzer, to break the source code into tokens. Asterisk parse tree construction asterisk the current parser only returns true or false. To build a parse tree, you would need to modify the parse_variable function to create and return tree nodes. Asterisk parser generators asterisk for more complex grammars, it's often easier to use a parser generator, like Antal, Yak, or Bison, to automatically generate the parser from a grammar specification. 8. Further topics, beyond Lecture 1 but relevant. Asterisk lexical analysis, tokenization the process of breaking the input source code into a stream of tokens. Asterisk syntax-directed translation asterisk attaching semantic actions to grammar rules to perform computations during parsing, example evaluating expressions. Asterisk intermediate code generation asterisk converting the parse tree into an intermediate representation that is easier to optimize and translate to machine code. Asterisk code optimization asterisk improving the intermediate code to make it more efficient. Asterisk code generation asterisk translating the intermediate code into machine code or assembly code. In summary asterisk. This tutorial provides a detailed introduction to context-free grammars, covering the fundamental concepts typically found in VTU's 18 CS54 Module 3, Lecture 1. It also includes a basic Python implementation of a recursive descent parser. Remember that this is just a starting point. To build a real-world parser, you'll need to explore more advanced techniques and tools. Good luck.